All right, welcome everyone. So today we are continuing to talk a little bit about expected value as well as variance. As far as announcements go, exam 1 is a week from now. So please be working on what you want on your 3" by 5" note card and working on some practice problems from Canvas. Hey Vivian. Based on what we're doing in class today, I recommend trying problems 4-18 and the third out-of-book problem after class today. And then on Thursday, we're going to be doing a combination of practice with expected value and variance using theoretical probability and practice with empirical probability. So if you can, please bring your laptops to class on Thursday. All right. So let's start with the problem where we left off last time. You'll recall we were looking at this probability distribution, probability mass function, of the possible numbers of products that could fail out of a set of 3 products that are being inspected. And we found that the expected number of failed products was 0.15. So now, suppose that each failed product costs $100 to fix, plus the inspector charges a flat $50 fee for inspecting a group of 3 products. And we want to find the expected cost of this overall process of the inspection. So we could do this in the same way that we did the problem yesterday. We could write out a table of the possible values of the cost, depending on whether 0, 1, 2, or 3 products failed. Align them with their probabilities. So the probabilities are going to be the same, just the number of the cost is going to be different. We could multiply the cost times the probability to get this third column, and then sum up that third column. But we could also do it in another way. Because what we're being asked to find is the expected value of 100 times y, if y is the number of failed products, plus 50. And that's a linear function of y, which is a random variable whose expected value we already know. So we can start by using theorem 3.5 to split up the expected value across the addition. And then we can use theorem 3.3 to say that the expected value of 50, well, 50 is a constant, so its expected value is just that same constant. And then we can use theorem 3.4 to say that we have this constant multiple inside the expected value. We can pull that constant outside. So we get 100 times the expected value of y plus 50. Often this process gets abbreviated. Do all 3 steps at the same time. So just say the expected value of 100y plus 50 equals 100 times the expected value of y plus 50. And you could say by theorems 3.3 through 3.5, or I'll often abbreviate it as by the linearity of expected value. So when we do this, we can now use the expected value of y that we found yesterday. We can plug that 1.15 in for the expected value of y, and now we can compute the expected cost as just 100 times 0.15 plus 50, so we get an expected cost of $65. So our interpretation here would be, if the inspector came every day and inspected 3 products every day for infinitely many days, our long run average cost would be $65 per day. Questions about this? Ooh, I think I forgot to up my volume. Let me make sure I can hear folks online. All right. So folks online, feel free to type something in the chat window or press the raise hand button. If you have questions, I should be able to hear you. All right. So now let's talk about variance. So variance describes the horizontal spread or variability of a distribution about its mean. And in probability, mean here is the same as expected value. So for example, here are 2 distributions of 2 different random variables that have the same expected value. So both of these distributions are centered at 10. But in this graph on the right, the possible values are much more spread out, far away from the mean. So this distribution on the right has higher variance compared to the distribution on the left, where the possible values tend to be much clustered, much closer to that central value, that expected value. So if we let the expected value of y have the symbol mu, then the variance of y has the formula of the expected value of the square of y minus mu. So this formula kind of makes sense with what we said variance should represent. That for every possible value of y in our distribution, we're taking the difference between that value and the mean mu, the expected value. We're squaring that so that they're all positive. We don't have positives and negatives canceling out. And then we take the expected value of that thing. So we take the average of the squared distance from the mean. And this is often given the symbol sigma squared for the variance. Two other measures of the spread or variability of a distribution to be aware of are the standard deviation, which often abbreviated SD, is just the square root of the variance. And it's often given the symbol sigma. So the square root of sigma squared is sigma. Makes sense. And for those of you who are planning on taking actuarial exam P, you'll want to be aware of the coefficient of variation. So this is the standard deviation divided by the mean. So we won't be using the coefficient of variation in this class, but it's good to have in your mind because it might come up on actuarial exam P. All right. So let's find the variance of y for this random variable where the values -1, 0, and 1 are all equally likely. And you'll recall yesterday we found that the expected value of this random variable is 0. So we can give that the symbol mu. So try using our formula for variance. You can use the fact that mu in this case equals 0. So if we plug in 0 for mu, we get the expected value of the quantity y minus 0, quantity squared. So that's the expected value of y squared. Anybody have in their notes from yesterday what that was? Kyle, what was it? Yeah, it was 2/3. And remember that we found that by making a new version of our table of our probability distribution with the values of y squared, then multiplying each row and then adding the results. So our variance here is 2/3. All right. Notice in this case, the variance of y was 2/3, and that was our expected value of y squared, which was 2/3, minus the square of the expected value, so minus 0 squared. Let's show that this property is going to hold in general. So let's start with our definition of variance and just sort of follow our nose using algebra. So let's start by squaring this factor in parentheses. So we can multiply that out using FOIL. So we get the expected value of y squared minus 2y mu plus mu squared. Any ideas about what we could do next to simplify this? Yeah, we can split this expected value up across the addition and subtraction. So we can turn this into the expected value of y squared plus the expected value of negative 2y mu plus the expected value of mu squared. So that's using theorem 3.5. And now, mu is a constant. We found the expected value of y. It's equal to some number. So that means that we can use theorems 3.3 and 3.4 to turn this expected value of a constant into just that constant and pull out the constant negative 2 times mu outside of the expected value. Kyle, would you mind putting your phone away, please? All right, so now we can apply the fact that the expected value of y equals mu to turn this expected value of y into mu. And now we can simplify this algebraically. So we have the expected value of y squared minus 2 mu squared plus mu squared. So the variance of y equals the expected value of y squared minus mu squared. Questions about this? All right, so this is theorem 3.6 in Wackerly. The variance of y equals the expected value of quantity y squared minus the square of the expected value of y. So this is often a faster way of computing variance than the original definition, depending on the specific problem. If you're like me, you may end up having trouble remembering the order of this subtraction. The way to think about this is to remember that variance is always non-negative. So if you think about an example like our negative 1, 0, 1 example, where we had the expected value of y equal to 0, but the expected value of y squared was positive, then we know we want to do the subtraction in the order positive minus 0, not 0 minus positive. All right, so let's do some important facts about variance. Again, let's let c be a constant. Then the variance of c equals 0. So that should kind of make sense if we think about variance as the horizontal variability around the expected value. If all we have is a constant, 100% of the time, it's equal to that constant. So there's no horizontal spread there. Second, the variance of a constant times y is equal to the constant squared times the variance of y. So when we pull constant multiples outside of variance, they get squared. And the variance of y plus a constant equals the variance of y. Proving that is the out-of-book problem on, third out-of-book problem on homework 3. All right, so to give you some ideas for how you might approach that out-of-book problem on homework 3, let's prove that first important fact. So let C be a constant. Let's prove that the variance of C equals 0. So let's start by writing out the variance of C. And let's do that using theorem 3.6 to write that in terms of the variance of some random variable equals the expected value of the square of that minus the square of its expected value. So we can just do that using C as our quote-unquote random variable. That's actually a constant. Any ideas about what theorem we might use next?
Where you say the E, like the previous one is like EC equals to C.
Yeah, the expected value of a constant equals a constant. So that's theorem 3.3. So that lets us turn the expected value of C into just C. And also, if C is a constant, then C squared is a constant. So we can turn the expected value of C squared into C squared. And now we have that the variance of C equals C squared minus quantity C squared. So that's 0. So something to point out here is a lot of these proofs, both about variance and about expected value, start from either the definition of expected value or variance, or one of our basic theorems. So theorem 3.6 is sort of an alternative way of defining a formula for variance. Or we saw theorem 3.2 yesterday was sort of an alternative way of thinking about expected value. And then they use some combination of high school algebra and theorems 3.3 through 3.5. So those are sort of your go-to tools when you're trying to prove something about expected value and variance. So let's try applying this idea to proving our third important fact, or second important fact, sorry, that the variance of C times Y, where C is a constant, equals C squared times the variance of Y. Try writing out what your first step in this proof is going to be. If you're using theorem 3.6, you're on the right track. So here's how I would start this proof. So using theorem 3.6 is sort of our alternative definition of variance. Writing out variance as the expected value of the square of the thing whose variance we want. So in this case, the square of the quantity c times y, minus the square of the expected value of the thing whose expected value, or the thing whose variance we want. Kyle. What's that? Oh yeah. All right. So who sees something that we can do to simplify this right-hand side of this equation?
Pull out the c squared.
So in this first term or the second term?
The first
In the first term? Yeah, we can apply the square to both of the things inside of the parentheses.
pull out the c.
And we can use theorem 3.3 to pull out, 3.4, to pull out that constant from the expected value that's in the parentheses of the second term. So here we've applied the square. Here we've used theorem 3.4 to pull the c outside of the expected value in the second term and pull the c squared out of the expected value in the first term. Now we can use some high school algebra again. So we can square each of the factors inside the parentheses of this second term. And then we can pull that outside of the, oh, never mind. Yeah, that's applying the square. And now we can factor the c squared.
And the one inside is b1.
Exactly. So using theorem 3.6 again, we can recognize this factor in the square brackets as being just another way of writing the variance of y. Questions about either of these proofs? Folks online, any questions so far? Mal says no. Anybody else? All right. Feel free to type in the chat window or hit that raise hand button if you think of questions. All right. So next, I'm going to switch over. On the Canvas site for our course, under week 3, you'll notice that there's an expected value.r script. So I'd like to demonstrate for you how we can use R to compute empirical expected values and variances. And let's do that using the example we've used in class of our random variable that's equally likely to take on each of the values -1, 0, and 1. So I'm going to start by creating a vector to store values of our random variable y. So I'm calling that stored. And I'm using the rep function to repeat or replicate copies of whatever comes first inside the function, a number of times equal to the second argument. So here I'm just using NA to represent a missing value, to say this is just an empty spot where we're going to store something later. And I'm making 1,000 copies of it. So we'll do our experiment, our simulation 1,000 times. So then I have this section that looks a lot like what we've done to compute empirical probabilities in the past. We have a for loop to do something 1,000 times. And inside the curly brackets for that for loop, we're performing the probability experiment. We're generating the random variable y. So in this case, I want a 1/3 probability that y equals -1, 0, and 1. And the way I'm going to do that is using the runif, the R uniform function, to generate one random number that's equally likely to be anywhere between 0 and 1. So if we just imagine a number line from 0 to 1, our variable u is equally likely to be anywhere in here. And then I'm going to divide that up into regions at 1/3 and 2/3. And I'll say if u is in this first region, then I'm going to say, if u is in here, then y is going to equal -1. So that's what we're doing here. We have an if statement. So if u is less than 1/3, then my random variable y equals -1. If u is in this next region between 1/3 and 2/3, y is going to equal 0. So we're doing that using the statement else if. So that means if it was not true that u was less than 1/3, so we didn't do the thing of assigning y to be equal to -1, then we check if u is less than 2/3. If that's true, then we set y equal to 0. So here we would be checking if u is anything less than 2/3, but we've already skipped over, we've already checked that whether u is less than 1/3. And if we made it to this else if, we know that u is not less than 1/3. So we know we're not in this first region of our number line. So this is just a concise way of saying if u is between 1/3 and 2/3, then we set y equal to 0. And then we use an else statement to say otherwise. So if both of these things that we tried checking were false, in that case, we must be in this third region of the number line between 2/3 and 1. Then we're going to set y equal to 1. All right. So what we've done the last 2 weeks would be after we figure out the value of y, then we would check something about it to determine if it was a success and add 1 to the number of successes. But what we're going to do here is we're just going to store the value of y in our variable called stored. And R uses square brackets to indicate which element of the vector to refer to. I'm going to change this to II because I like that syntax better now. So here, when II is 1, the first time through the loop, we're storing in the first entry in the vector. Then the second time through the loop, when II is 2, we're storing in the second entry in the vector, and so on, all the way up to when II equals 1000, we're storing in the last element of the vector. Questions about this part? Kyle?
So II variables don't mess with each other. So like, so the for loop saying II equals to 1. And then it's saying stored 1 equals y.
So no, because this line of stored II is referring to the ith position in stored. So it's changing stored, it's not changing the value of II. All right. So let's try running this. And then at the end, here we can use a similar square bracket notation to view a subset of our vector. Because we could just type stored to see everything that's in it, but maybe we don't want to look at all 1,000 numbers. If we just want to look at the first 10 entries, we can do 1:10 inside the square brackets. And what we're hoping to see here is values of -1, 0, and 1, because those are the things that are valid values for our random variable. Yeah, that looks good. We can check out some other possibilities, say 990 to 1,000. Yep, those are also -1s, 0s, and 1s. So it looks like we successfully stored y in each of the positions. All right. Now we can use these 3 functions, mean to find the average or expected value, VAR to find the variance, and SD to find the standard deviation. So let's enter in the mean here, the expected value. What are we hoping this will be close to? Kyle? Yeah, we hope it should be close to 0 because we found our theoretical expected value of this random variable was 0. Hey, in this case it was exactly 0. If we do it again, we should get some variation. .013. So not exactly 0, but pretty close. So notice what this is doing is it's representing one of our interpretations of expected value. That one of our interpretations of expected value is that it's the long run average result of this random variable. If we repeat throwing the dice or spinning the spinner or whatever it is infinitely many times, the mean should be 0. So what we're doing here is, well, we can't do it infinitely many times. Let's do it 1,000 times. So we don't expect the mean to be exactly 0. This is just a sample out of the infinitely many times we could do it. But it is close to what we expect to get in the long run. All right. How about the variance? What are we hoping to be close to for this? Not 1. What was the variance that we found for the 1/3, 1/3, 1/3 example? Okay. 2/3, yeah. So let's check it. So 0.653, so pretty close to 0.6 repeating. How about the standard deviation? What do we hope this will be close to? The square root of 2/3, which we can check what that is. SQRT of 2/3. So we're hoping to be close to 0.8164, 0.8083. Questions about this empirical expected value and variance?
So in bars studio, the mean, variance, and standard, it's their code for that, right?
Yep. So just the word mean, VAR for the variance, and SD for the standard deviation. Any questions from folks online? All right. So we have 7 minutes left. Let's try doing a problem involving closer to real life application of expected value and standard deviation. So this is the activity marked variance under week 3. And we have a letter. Now, let me go ahead and download this so that I can make it bigger. To a fictional company called Probability R Us. So take your time to read this letter. Make it bigger. So what does expected value have to do with this letter? Okay.
The expected value of the stocks after a year of investment.
Yeah, we want to know the expected value of the stocks after a year of investment, or the expected return, given the probability statements about what happens to the economy. So go ahead and try computing either the expected value of the stocks or the expected return under this scenario. And folks online, please do write down your responses about this, and then you can turn those in on Canvas. Folks who are here in person, I have marked down that you're working on this, so you don't need to turn in your work. So our first question is, what does expected value have to do with this problem? And we found that if we're trying to decide which stock we should buy, we might want to pick the stock that has the higher expected return. So right now we're computing the expected return of the two stocks. Sam, question? Are you getting an unexpected result?
No, it's weird to like multiply the percents by the percents.
Good question. So these percents that are probabilities, I would go ahead and convert those to decimals. The percents that are returns, you could treat as percentages as they are, with like decrease by 8.8% being a negative, or you could relate them to a value of 1, so then like increasing by 2% would be 1.02, decreasing by 8.8% would be 0.922, 0.972. Either way of those works. Or you could use the fact that he's planning to invest $1,000 and do it in terms of, if it increases in value by 2%, then he'll have 1,000 times $1.02. All right, so we are out of time. We will finish this activity on Thursday, and then we'll do some additional practice with both theoretical and empirical expected value and variance. I will see you then.
So are we not discussing,
What's that?
so are we not discussing that question?
Yep, we're gonna discuss this at the start of class on Thursday.